Now let's talk about function calls. Function calls are useful to make our program more modular, so we can kind of encapsulate our functions in modules that have defined inputs and defined outputs. And we have a caller function. This is the one that's doing the calling. And a callee is the function that's called, the callee function. So in this case, we have the caller function, which is main, is the caller, and then which is doing the calling right here, to the callee, the function being called, which is sum. So sum is being called. And here we have this keyword before the function name. So here's our function name sum, and we have this keyword. This says what kind of value it's going to return. So it's going to return a 32-bit value. How do we want to interpret it? In this case, as a signed integer or 2's complement integer. If we had put unsigned in, we would have interpreted that 32-bit value that it returned as an unsigned integer. And then we also have input arguments, in this case A and B, and here's where we return the value. So it adds them together and says, hey, this is the value I want to return. So here, when it returns here, y is going to be equal to, well, whatever a plus b is, in this case 49. So after this completes, y is going to be equal to the sum of a plus b, which is 49. So let's show a simple function call in assembly language to start with. So here's our caller function. Our main function is calling our callee function simple. And you can see in this case, simple, inside those parentheses, there's nothing there. So it doesn't actually have any input arguments, and it doesn't return anything. So this void here means that simple doesn't have a return value, it just returns. It just doesn't say return A or return 17 or return some value. It's just returning. And so this is the simplest function call because it actually doesn't do anything. But the way we do this in RISC-V assembly is we do a jump and link instruction. This does the call to simple. So it almost looks like a jump. We've seen jump instructions before. Almost looks like that, where we just jump to the simple label, which is, has another instruction there. But it has this extra thing, and link. So jump and link, well, does the usual jump, jumps to the simple label, as we expected. But it also stores PC+4 into register RA. And here we go, PC+4. Well, the PC is the program counter, and it keeps track, it holds the current value of the address being executed. So our instructions are also stored in memory, just like our data. So we have instruction, the jump and link instruction, it's a 32-bit instruction, and so it takes up 4 bytes. So the next instruction is at hex 304, the next one would be at hex 308, and so on. And so this PC tells us, well, this program counter tells us which instruction is currently executing. And in this case, PC is equal to hex 300 when the jump and link instruction is executing. So PC+4 is, so PC is here. PC, if we add 4 to it, is the next instruction at 304. And so we make this RA register, the return address register. Return address, the RA register stands for return address, because that's where we want to return to. After this function is called, then when it returns, it needs to return to continue executing the next code. And so jump and link both jumps to the label and links RA equals PC+4. And it does that so that when it returns, this return in the high-level code is executed by executing the jump register instruction. So this jumps to JR jump register, jumps to a value held in RA. And we know what value that is. That value is hex 304. And so that we have jump register to that value, well, that's the address, hex 304, so it jumps to the instruction at that address. So when we call functions and return, we have calling conventions. A convention is something we all agree on. And why is that important? Well, it's important because if someone's writing code in one place, and another person is writing code, their code can work together because we're all agreeing on the same convention. So the caller agrees to pass arguments to the callee and then jump to the callee. The callee performs the function, returns to the caller to the point of call, specifically PC+4, but it must not overwrite registers or memory needed by the caller. So it can't, right? It's like the caller says, oh, I have my own stuff. Maybe it's using S0, S1, S2, it has stuff in it. And then it makes the call to some other function, the callee. If the callee writes over S0, S1, S2, when it returns JRRA, guess what? S0, S1, and S2 no longer have those values. So that's a problem. So let's talk about each of these conventions. Passing arguments to the callee, how we do that, how to return to the caller, we talked about that, and this overwriting of registers, or avoiding overwriting registers or memory needed by the caller. So the way that we call a function is using our jump and link instruction, return from a function, jump register RA. And now we're going to agree on, again, this is a convention, putting the arguments in these argument registers, argument 0 through argument 7. And then the callee will put its return value, if it has one, into register A0. So A0 is used, kind of doubles, is used for both arguments, input arguments, and the return value. And so let's talk about how the functions do this. Here's some code where we're calling, so main, the caller is calling this diff of sums function and puts in these input arguments 2, 3, 4, and 5. And then diff of sums returns an integer, so a signed 32-bit value. And it returns it by this high-level code return, and this is the value it wants to return. And so in RISC-V, we're going to put the arguments starting with A0. So the leftmost argument goes into register A0, next one A1, next one A2, next one A3. If we had more, we go up to 7 arguments. And then there are ways to put more arguments, which we'll talk about later, store the rest of them in memory. And then this diff of sums performs the operation, right? 2 plus 3, here's F and G, 2 plus 3, just in that order. So 5 minus 4 plus 5, 5 minus 9, we're going to return the value minus 4. And so the way that is done is by putting that value, the result, into A0. So A0 will get the value, in this case, minus 4, whatever result is. So here's some RISC-V assembly code performing this operation. So these first 4 instructions put the arguments into, well, A0, 2 goes into A0, 3 goes into A1. These were our arguments to the diff of sums function. So before the call is made, we have to set it up and put the arguments in the registers that are expected by the callee, A0 through A7 in this case, using just A0 through A3. And only then is the call made, jump and link diff of sums. So it jumps to a diff of sums label. It does its thing by, well, performing F plus G, put that in T0, H plus I, and then subtracting those two, T0 minus T1. And then finally, this last one is putting the result, T3, into the return value, or the return register, so that when this function returns JRRA, it's going to jump to the instruction right after the call instruction, that jump and link diff of sums, and it's expecting, well, that return value in A0. So y was in S7, so it's going to say y equals whatever value is returned. It's kind of this agreed upon use of the registers, where it's like saying, okay, I'm gonna put that letter, under the park bench, on whatever park it is, and we agree that that's where I'm gonna put it, and you're gonna come and get it. Right? We agree that, hey, this return value is gonna be put in A0 by the callee, and so that the caller knows where to find it. And same thing with the argument registers. The caller is going to put those, before making the call, in some specified registers, in this case the argument registers, so that the callee knows where to find its arguments when it performs its function. So one thing to note is that jump and link diff of sums is what's called pseudocode. And pseudocode is code that's useful for the programmer, but not real MIPS assembly code. So jump and link diff of sums is pseudocode for jump and link RA, which is where PC+4 should go, and then the label. So this is a real RISC-V instruction, but this is, most usually that's how we use jump and link. And so we made a pseudocode, or RISC-V decided to make a pseudocode instruction for that, so that we don't have to have extra baggage of, well, it's usually RA. We could actually put any register there, jump and link, put PC+4 and S0, but we rarely do that. So there's a bit of an issue here. In our code, diff of sums, that the function, the callee function, overwrote 3 registers, T0, T1, and S3. But if the main function, the caller, was using those registers and wants to use the values that it had in those registers after the call, they just got overwritten. And so this is a bit of a problem, but we can use the stack, which is a small amount of memory, to temporarily store the original values that were in T0, T1, and S3 when the function was called, overwrite them, and then restore those values from memory right before returning from the diff of sums function.